In mathematics, computer science and operations research, mathematical optimization is the selection of a best element from some set of available alternatives. In the simplest case, an optimization problem consists of maximizing or minimizing a real function by systematically choosing input values from within an allowed set and computing the value of the function. The generalization of optimization theory and techniques to other formulations comprises a large area of applied mathematics. More generally, optimization includes finding best available values of some objective function given a defined domain, including a variety of different types of objective functions and different types of domains. Optimization problems. An optimization problem can be represented in the following way. Given a function f, a from some set A to the real numbers sought, an element x0 in A such that ff for all x in A or such that ff for all x in A. Such a formulation is called an optimization problem or a mathematical programming problem. Many real-world and theoretical problems may be modeled in this general framework. Problems formulated using this technique in the fields of physics and computer vision may refer to the technique as energy minimization. Speaking of the value of the function f as representing the energy of the system being modeled, typically, A is some subset of the Euclidean space Rn, often specified by a set of constraints, equalities or inequalities that the members of A have to satisfy. The domain A of f is called the search space or the choice set, while the elements of A are called candidate solutions or feasible solutions. The function f is called, variously, an objective function, a loss function or cost function, a utility function or fitness function, or, in certain fields, an energy function or energy functional. A feasible solution that minimizes the objective function is called an optimal solution. In mathematics convention, optimization problems are usually stated in terms of minimization. Generally, unless both the objective function and the feasible region are convex in a minimization problem, there may be several local minima. A local minimum x** is defined as a point for which there exists some delta greater than 0 so that for all x such that the expression holds, that is to say, on some region around x** all of the function values are greater than or equal to the value at that point. Local maxima are defined similarly. A large number of algorithms proposed for solving non-convex problems, including the majority of commercially available solvers, are not capable of making a distinction between local optimal solutions and rigorous optimal solutions, and will treat the former as actual solutions to the original problem. The branch of applied mathematics and numerical analysis that is concerned with the development of deterministic algorithms that are capable of guaranteeing convergence in finite time to the actual optimal solution of a non-convex problem is called global optimization. Notation. Optimization problems are often expressed with special notation. Here are some examples. Minimum and maximum value of a function. Consider the following notation. This denotes the minimum value of the objective function, when choosing x from the set of real numbers. The minimum value in this case is occurring that. Similarly, the notation asks for the maximum value of the objective function 2x, where x may be any real number. In this case, there is no such maximum as the objective function is unbounded, so the answer is infinity or undefined. Optimal input arguments. Consider the following notation, or equivalently this represents the value of the argument text in the interval that minimizes the objective function x2 plus 1. In this case, the answer is x equals -1, since x equals 0 is infeasible, i.e., does not belong to the feasible set. Similarly, or equivalently represents the pair that maximizes the value of the objective function, with the added constraint that x lie in the interval. In this case, the solutions are the pairs of the form and pi, where k ranges over all integers. Argmin and argmax are sometimes also written argmin and argmax, and stand for argument of the minimum and argument of the maximum. History. Fermat and Lagrange found calculus-based formulas for identifying optima, while Newton and Gauss proposed iterative methods for moving towards an optimum. The term linear programming for certain optimization cases was due to George B. Dantzig, although much of the theory had been introduced by Leonid Kantorovich in 1939. Dantzig published the simplex algorithm in 1947, and John von Neumann developed the theory of duality in the same year. Other major researchers in mathematical optimization include the following: Richard Bellman, Roger Fletcher, Ronald A. Howard, Fritz John, Narendra Karmarkar, William Karush, Leonid Kharchian, Bernard Koopman, Harold Kuhn, Laszlo Lovász, Arkady Nemirovsky, Yuri Nesterov, Boris Polyarch, Lev Pontryagin, James Reniger, R. Tyrrell Rockefeller, Cornelis Roos, Naum Z. Shaw, Michael J. Todd, Albert Tucker. Major subfields. Convex programming studies the case when the objective function is convex or concave and the constraint set is convex. This can be viewed as a particular case of nonlinear programming or as generalization of linear or convex quadratic programming. Linear programming, a type of convex programming, studies the case in which the objective function f is linear and the constraints are specified using only linear equalities and inequalities. Such a set is called a polyhedron or a polytope if it is bounded. Second-order cone programming is a convex program, and includes certain types of quadratic programs. Semi-definite programming is a subfield of convex optimization where the underlying variables are semi-definite matrices. It is generalization of linear and convex quadratic programming. Conic programming is a general form of convex programming. LP, SOCP and SDP can all be viewed as conic programs with the appropriate type of cone. Geometric programming is a technique whereby objective and inequality constraints expressed as polynomials and equality constraints as monomials can be transformed into a convex program. Integer programming studies linear programs in which some or all variables are constrained to take on integer values. This is not convex, and in general much more difficult than regular linear programming. Quadratic programming allows the objective function to have quadratic terms, while the feasible set must be specified with linear equalities and inequalities. For specific forms of the quadratic term, this is a type of convex programming. Fractional programming studies optimization of ratios of two nonlinear functions. The special class of concave fractional programs can be transformed to a convex optimization problem. Nonlinear programming studies the general case in which the objective function or the constraints or both contain nonlinear parts. This may or may not be a convex program. In general, whether the program is convex affects the difficulty of solving it. Stochastic programming studies the case in which some of the constraints or parameters depend on random variables. Robust programming is, like stochastic programming, an attempt to capture uncertainty in the data underlying the optimization problem. Robust optimization targets to find solutions that are valid under all possible realizations of the uncertainties. Combinatorial optimization is concerned with problems where the set of feasible solutions is discrete or can be reduced to a discrete one. Stochastic optimization for use with random function measurements or random inputs in the search process. Infinite-dimensional optimization studies the case when the set of feasible solutions is a subset of an infinite-dimensional space, such as a space of functions. Heuristics and meta-heuristics make few or no assumptions about the problem being optimized. Usually, heuristics do not guarantee that any optimal solution need be found. On the other hand, heuristics are used to find approximate solutions for many complicated optimization problems. Constraint satisfaction studies the case in which the objective function f is constant. Constraint programming. Disjunctive programming is used where at least one constraint must be satisfied but not all. It is of particular use in scheduling. In a number of subfields, the techniques are designed primarily for optimization in dynamic contexts. Calculus of variations seeks to optimize an action integral over some space to an extremum by varying a function of the coordinates. Optimal control theory is a generalization of the calculus of variations which introduces control policies. Dynamic programming studies the case in which the optimization strategy is based on splitting the problem into smaller subproblems. The equation that describes the relationship between these subproblems is called the Bellman equation. Mathematical programming with equilibrium constraints is where the constraints include variational inequalities or complementarities. Multi-objective optimization. Adding more than one objective to an optimization problem adds complexity. For example, to optimize a structural design, one would desire a design that is both light and rigid. When two objectives conflict, a trade-off must be created. There may be one lightest design, one stiffest design, and an infinite number of designs that is some compromise of weight and rigidity. The set of trade-off designs that cannot be improved upon according to one criterion without hurting another criterion is known as the Pareto set. The curve created plotting weight against stiffness of the best designs is known as the Pareto frontier. A design is judged to be Pareto optimal if it is not dominated by any other design. If it is worse than another design in some respects and no better in any respect, then it is dominated and is not Pareto optimal. The choice among Pareto optimal solutions to determine the favorite solution is delegated to the decision maker. In other words, defining the problem as multi-objective optimization signals that some information is missing. Desirable objectives are given but not their detailed combination. In some cases, the missing information can be derived by interactive sessions with the decision maker. Multi-objective optimization problems have been generalized further into vector optimization problems where the ordering is no longer given by the Pareto ordering. Multimodal optimization problems are often multimodal, that is, they possess multiple good solutions. They could all be globally good or there could be a mix of globally good and locally good solutions. Obtaining all the multiple solutions is the goal of a multimodal optimizer. Classical optimization techniques, due to their iterative approach, do not perform satisfactorily when they are used to obtain multiple solutions, since it is not guaranteed that different solutions will be obtained even with different starting points in multiple runs of the algorithm. Evolutionary algorithms are, however, a very popular approach to obtain multiple solutions in a multimodal optimization task. Classification of critical points and extrema. Feasibility problem. The satisfiability problem, also called the feasibility problem, is just the problem of finding any feasible solution at all without regard to objective value. This can be regarded as the special case of mathematical optimization where the objective value is the same for every solution, and thus any solution is optimal. Many optimization algorithms need to start from a feasible point. One way to obtain such a point is to relax the feasibility conditions using a slack variable. With enough slack, any starting point is feasible. Then, minimize that slack variable until slack is null or negative. Existence. The extreme value theorem of Carl-Weierstrass states that a continuous real-valued function on a compact set attains its maximum in minimum value. More generally, a lower semi-continuous function on a compact set attains its minimum. An upper semi-continuous function on a compact set attains its maximum. Necessary conditions for optimality. One of Fermat's theorems states that optima of unconstrained problems are found at stationary points, where the first derivative or the gradient of the objective function is zero. More generally, they may be found at critical points, where the first derivative or gradient of the objective function is zero or is undefined, or on the boundary of the choice set. An equation stating that the first derivative equals 0 at an interior optimum is called the first-order condition, or a set of first-order conditions. Optima of equality-constrained problems can be found by the Lagrange multiplier method. The optima of problems with equality or inequality constraints can be found using the Karush-Kuhn-Tucker conditions. Sufficient conditions for optimality, while the first derivative test identifies points that might be extrema. This test does not distinguish a point that is a minimum from one that is a maximum, or one that is neither. When the objective function is twice differentiable, these cases can be distinguished by checking the second derivative or the matrix of second derivatives in unconstrained problems, or the matrix of second derivatives of the objective function and the constraints called the bordered Hessian in constrained problems. The conditions that distinguish maxima or minima from other stationary points are called second-order conditions. If a candidate's solution satisfies the first-order conditions, then satisfaction of the second-order conditions as well is sufficient to establish at least local optimality. Sensitivity and continuity of optima. The envelope theorem describes how the value of an optimal solution changes when an underlying parameter changes. The process of computing this change is called comparative statics. The maximum theorem of Claude-Berge describes the continuity of an optimal solution as a function of underlying parameters. Calculus of optimization for unconstrained problems with twice differentiable functions. Some critical points can be found by finding the points where the gradient of the objective function is 0. More generally, a zero subgradient certifies that a local minimum has been found for minimization problems with convex functions and other locally Lipschitz functions. Further, critical points can be classified using the definiteness of the Hessian matrix. If the Hessian is positive definite at a critical point, then the point is a local minimum. If the Hessian matrix is negative definite, then the point is a local maximum. Finally, if indefinite, then the point is some kind of saddle point. Constrained problems can often be transformed into unconstrained problems with the help of Lagrange multipliers. Lagrangian relaxation can also provide approximate solutions to difficult constrained problems. When the objective function is convex, then any local minimum will also be a global minimum. There exist efficient numerical techniques for minimizing convex functions, such as interior point methods.